The James Webb Space Telescope opened its eyes in July 2022, the most powerful observatory ever built, designed to see the first galaxies, the first stars, the earliest moments of cosmic history. Scientists expected to find small, primitive galaxies, faint blobs of light from the universe's infancy. What they found instead defies explanation. Galaxies that should not exist, not just unusual, impossible according to every model we have. The first images came back, stunning, beautiful. Then astronomers started measuring, calculating distances, determining masses. The numbers made no sense. JWST was detecting massive, mature galaxies at redshifts above 10. This means light travelling for over 13 billion years, from when the universe was less than 500 million years old. At that time, galaxies should be small, irregular, just beginning to form. These galaxies were not small. They were enormous, comparable to the Milky Way, with billions of stars already formed, already organised into spiral structures, already containing supermassive black holes. This violates everything we know about galaxy formation. The universe at 500 million years old was too young. Not enough time had passed. Stars need time to form. Galaxies need time to assemble. Black holes need time to grow. Yet here they were, fully formed, mature, existing impossibly early. One galaxy, JWST 13, sits at redshift 13.2 light-years. It existed 330 million years after the Big Bang. It contains 1 billion solar masses, already assembled into a coherent structure. Standard models say this is impossible. The galaxy would need to form stars at impossible rates, convert gas to stars faster than physics allows. Even if every single atom of gas in that region became stars, even if the process was 100% efficient, there is not enough time. Another galaxy, CEERS 93316, initially appeared to be at redshift 16.7. This would place it at 250 million years after the Big Bang. Measurements showed a mass of 100 billion solar masses, more massive than the Milky Way, existing when the universe was barely beginning. Later analysis suggested this particular galaxy might be at a lower redshift, closer, less impossible. But more keep being found. Dozens of massive galaxies at redshifts where they should not exist, all breaking the rules. Some astronomers proposed the measurements were wrong, that dust was making distant galaxies appear redder, that we were misidentifying their distances, but spectroscopic follow-up confirmed them. These are genuinely ancient galaxies, genuinely massive, genuinely impossible. Others suggested the galaxies are not as massive as they appear, that we are misinterpreting the light, that unusual stellar populations could make small galaxies look big. But the evidence grows stronger with each observation. These galaxies are real, they are massive, they are there. The crisis is not exaggeration. Leading cosmologists are calling this the biggest challenge to the standard model of cosmology in decades. Some are saying we need to rethink everything. Galaxy formation, dark matter, the early universe, all of it. Because what JWST sees does not fit, cannot fit, requires physics we do not have. The lambda CDM model, our standard cosmology, predicts galaxy formation rates, star formation rates, how quickly structure emerges from the uniform early universe. The model has been tested extensively. It matches observations of the cosmic microwave background, matches large-scale structure, matches galaxy distributions in the recent universe. But it does not match what JWST sees at high redshift. Not even close. The galaxies are too big, too massive, too mature, by factors of 10 or more. This is not a small discrepancy. It is a fundamental breakdown. One possibility is that star formation in the early universe was vastly more efficient than we thought, that the first stars formed faster, burned brighter, created more heavy elements, seeded more star formation in a runaway process. But efficiency has limits. Physics has limits. Even maximally efficient star formation cannot explain what we see. Another possibility is that dark matter behaves differently than we thought, that it clumps more strongly in the early universe, creates deeper gravitational wells, pulls gas together faster, accelerates galaxy formation. This would require modifying our understanding of dark matter. Perhaps it is not cold. Perhaps it has self-interactions we have not accounted for. Perhaps it is not even the particle we think it is. Some physicists have proposed primordial black holes as an explanation. If black holes formed in the Big Bang, they would act as seeds. Galaxies would assemble around them faster, grow more quickly, reach large masses earlier. But this requires enormous numbers of primordial black holes, more than other observations allow. The tension is real, the problem is severe, and it gets worse. Because the impossible galaxies are not the only thing JWST found. There are the impossible stars, red giants in these early galaxies, stars that should take billions of years to evolve, existing when the universe was hundreds of millions of years old. Stellar evolution is well understood. We know how long it takes for stars to age, for them to swell into red giants, for them to die. Yet JWST sees evolved stars in the earliest galaxies, stars that are already old when the universe is young. Then there are the supermassive black holes, quasars at redshift 10 and beyond, black holes with millions or billions of solar masses. Existing when the universe was a fraction of its current age, black holes grow by accreting matter, by consuming gas and stars. The process has a speed limit, the Eddington limit. Accrete too fast and radiation pressure blows away the infalling matter. Growth stalls. Supermassive black holes need time to grow, millions of years, hundreds of millions, starting from stellar mass seeds and building up. But JWST sees them already supermassive incredibly early. Too early to have grown from stellar mass seeds. This suggests they formed differently. Direct collapse. Gas clouds collapsing straight into massive black holes without forming stars first. Or they formed from population 3 stars, the first stars, which were more massive than modern stars, dying and leaving behind heavier black hole seeds. But even this struggles to explain the observations. The black holes are too massive, too early. Something is missing. Some process we do not understand. Some physics operating in the early universe that we have not accounted for. JWST was supposed to confirm our models, show us the first galaxies forming just as simulations predicted. Instead, it showed us galaxies that should not exist. Black holes that should not exist. Stars that should not exist. All there. All real. All demanding explanation. This is not malfunction. Not error. Multiple teams have analysed the data. Different methods. Different assumptions. All reach the same conclusion. The early universe was not what we thought, and we need new physics to explain it. Light from distant galaxies takes time to reach us. The farther away something is, the longer the light has travelled. When we look at a galaxy 10 billion light years away, we see it as it was 10 billion years ago. The light left that galaxy when the universe was young, travelled through expanding space, arrived here today. JWST looks farther than ever before, sees galaxies from when the universe was less than 5% of its current age. The light from these galaxies should look young, blue, the light of hot, young stars, short-lived massive stars that burn bright and die fast. This is what early galaxies should contain. Population 3 stars maybe, or at least population 2. Low metallicity stars formed from pristine gas. Their light should be distinctly blue, but JWST sees red light. Lots of it. From galaxies that are impossibly old. The light tells a story. Spectra break down into components, different wavelengths, different elements, different stellar populations. When you analyse the spectra from these early galaxies, you find old stars, red giants, stars that have evolved, stars that should not exist yet. The Balmer break is one indicator. This is a feature in stellar spectra caused by hydrogen absorption. Its strength tells you the temperature of stars. Young, hot stars have weak Balmer breaks. Old, cool stars have strong ones. JWST sees strong Balmer breaks in galaxies at redshift 10 and above. This means old stars, evolved stars, stars that have been around for billions of years. But the universe itself is not billions of years old at that point. It is hundreds of millions of years old. How can the stars be older than the universe? They cannot. Yet the spectra say they are. This is the old light problem. And it is not just one or two galaxies. It is systemic. Galaxy after galaxy, showing signs of old stellar populations. Too old, too evolved, too red. One explanation is dust. Dust absorbs blue light, lets red light through. This makes young galaxies look old, reddened by intervening dust. This is possible, but the amount of dust required is enormous. Dust is made from heavy elements: carbon, silicon, iron. These come from stars, from supernovae. You need multiple generations of stars to produce significant dust. How do you get that much dust in the early universe? You need stars to form, live, die, explode, produce dust. Then more stars form from the enriched gas, live, die, produce more dust. This takes time, billions of years typically. Yet JWST sees dusty galaxies at redshifts where there has not been enough time. The dust itself is impossible. Another explanation is that we are misidentifying the redshifts, that these galaxies are not as distant as we think, that they are closer. Their red light is intrinsic, not a sign of old stars but something else. But spectroscopic measurements confirm the distances. Multiple emission lines, clear redshift signatures. These galaxies are genuinely distant, genuinely early. There is also the possibility of unusual stellar populations. Perhaps the first stars were different than we model. Perhaps they evolved faster, reached red giant phase in hundreds of millions of years instead of billions. But stellar evolution is physics, well-tested physics. Stars burn fuel at rates determined by nuclear reactions. Massive stars burn fast, live short lives. Low-mass stars burn slow or ho, live long lives. There is no known way to make stars evolve faster than the physics allows. Yet JWST requires exactly that. Stars aging impossibly fast, or stars that were already old when they formed, which makes no sense. Some researchers have proposed that time itself behaved differently in the early universe, that clocks ran faster, that physical processes operated on different timescales. This is exotic. It requires modifying general relativity, or invoking quantum gravity effects, or suggesting the universe went through phase transitions that altered the flow of time. There is no evidence for this beyond the JWST observations, no theoretical framework that predicts it, just speculation driven by the need to explain the data. Then there is the metallicity problem. Metallicity means heavy elements, anything heavier than helium. The first stars formed from pure hydrogen and helium. They had zero metallicity. When they died, they enriched the gas, created carbon, oxygen, iron, all the elements we are made of. Second-generation stars formed from enriched gas. They had some metallicity. Not much, but some. Over billions of years, generation after generation, metallicity increased. The Milky Way today has high metallicity. We are made from elements created in stars that died long ago. JWST should see low metallicity in early galaxies, near zero, because there has not been time for multiple generations. But JWST sees solar metallicity, or higher, galaxies with as much heavy elements as the Milky Way. Existing when the universe is less than 1 billion years old, this is impossible. You cannot create solar metallicity that fast. You need many stellar generations, many supernovae, many cycles of enrichment. Even if stars formed at impossible rates, even if supernovae occurred constantly, there is not enough time. The elements themselves cannot be produced fast enough. Nucleosynthesis has limits. Each supernova produces specific amounts of specific elements. You can calculate how many supernovae are needed to reach solar metallicity. The number is large. The time required is billions of years. Yet JWST sees it accomplished in hundreds of millions. Some scientists are questioning whether our understanding of nucleosynthesis is complete, whether there are processes in the early universe that produce heavy elements faster. Supermassive stars collapsing directly to black holes but ejecting processed material first. Pair instability supernovae, producing more heavy elements than standard supernovae. Exotic mechanisms we have not considered. But these are speculative, invented to explain the observations, not predicted by existing theory. The old light problem extends to galaxy morphology. Early galaxies should be irregular, chaotic, blobs of stars without structure. Spiral arms take time to develop, require differential rotation, disk settling, gravitational interactions. These processes take billions of years. Yet JWST sees spiral galaxies at redshift 10, organized, structured, with clear arms, bars, bulges, features that should not exist yet. Disk galaxies need to settle. Gas needs to collapse into a rotating disk. Stars need to form in that disk. Spiral density waves need to develop. All of this takes time, more time than has passed. Yet there they are, spiral galaxies, in the infant universe, looking mature, looking old, looking impossible. The light reaching us from the early universe tells a story we do not understand. A story of galaxies that are too old, too evolved, too structured, too enriched, all existing too early. The light does not lie, but it describes a universe that does not fit our models, and we do not know why. The universe has a horizon, not a physical edge, but a limit to what we can see. Light travels at a finite speed. The universe has a finite age. Light from beyond a certain distance has not had time to reach us yet. We call this the cosmic horizon. It sits at about 46 billion light-years away. Beyond it, the universe exists, but we cannot see it. Light from there has not reached us. Will never reach us because space expands. JWST was designed to look close to this horizon, to see the most distant objects possible, the earliest galaxies, the first light. But something strange appeared in the data. Objects that seem to violate the horizon. That should not be visible. That should not exist where we see them. These are not galaxies exactly. They are anomalies, faint signals, patterns in the data, features that do not fit any known astrophysical object. Some appear at redshifts above 20. This corresponds to times less than 200 million years after the Big Bang. We should be approaching the Dark Ages, the period before the first stars formed. We should see nothing there. Yet JWST detects signals, faint, but real, confirmed by multiple observations, not instrument noise, not cosmic rays. Something is there, emitting light, from an era that should be dark. One interpretation is that these are population 3 stars, the first stars, forming earlier than we thought, lighting up the universe, ending the Dark Ages sooner than models predict. But population 3 stars should be individual objects, or small clusters. These signals are too uniform, too spread out, covering large areas of the sky, not point sources like stars, extended emission like galaxies, but galaxies that should not exist yet. Another signal appears at negative redshift. This makes no sense. Negative redshift means blue shift, objects moving toward us. But in an expanding universe, everything should be redshifted, moving away. Blue shift is possible for nearby objects. Local motion can overcome cosmic expansion. But these signals are not nearby. They have other characteristics suggesting great distance, yet they are blue shifted, moving toward us. This defies cosmology. In an expanding universe, distant objects recede, always. Hubble's law. The farther away, the faster the recession. Negative redshift should not appear at cosmological distances. Some astronomers think this is a calibration error, that the data is misinterpreted, that the signals are foreground objects, nearby stars or asteroids contaminating the field. But the signals persist. Different fields, different observations, always the same pattern. Objects that should not be blue shifted, but are. Then there are the signals from outside observable patches. The universe is not entirely uniform. It has structure, regions denser than others, voids, filaments, clusters. These structures are causally connected. Light from one part can reach other parts, but there are limits. Regions separated by more than the horizon distance cannot have exchanged information, cannot be correlated. Yet JWST sees correlations across the horizon, patterns extending beyond causal contact, features in one part of the sky matching features in another part, too far apart to be connected, too similar to be coincidence. The cosmic microwave background shows similar anomalies, temperature fluctuations on scales larger than the horizon, features that should not be correlated, but are. JWST adds to this. Galactic distributions, structures, alignments, all showing patterns beyond the horizon. This suggests something is wrong with our understanding. Either the horizon is larger than we think, or information travels faster than light, or the early universe had unusual properties that allowed correlations to form before inflation. Some cosmologists invoke inflation, the rapid expansion of the early universe. Inflation stretched quantum fluctuations to cosmic scales, created the seeds of structure. But inflation should also erase correlations beyond the horizon. Unless inflation ended differently than we model, unless there were multiple epochs, unless the scalar field driving inflation had unusual properties. Others propose that the universe is cyclic, that the Big Bang was not the beginning, that a previous universe existed, collapsed, bounced, began expanding again. Information from the previous cycle carried through, creating correlations we see today. This is exotic, requires new physics. But it explains the observations. There are also suggestions that we are seeing quantum effects, that the universe at very early times was small enough for quantum mechanics to matter. Entanglement across the universe. Correlations created by quantum fluctuations, persisting into the classical era, visible today as patterns beyond the horizon. Then there are the truly strange signals, objects that appear and disappear, present in one observation, gone in the next, not supernovae, not transients, just vanishing, as if they flicker in and out of existence. These could be gravitational lensing events, a foreground object magnifying background objects, then moving away. The magnification disappears, the background object fades. This is possible, but the frequency is wrong. Too many flickering objects, too many disappearances. The models do not predict this rate. Some researchers speculate about observers' effects. That quantum mechanics operates on cosmological scales. That observation collapses wave functions. That objects exist in superposition until measured. That JWST's observations are creating reality rather than revealing it. This is fringe, not mainstream. But the data is strange enough that even fringe ideas get attention. The most disturbing possibility is that we are seeing outside our universe, that the cosmic horizon is not a hard boundary. That information leaks through from other regions, other bubble universes, other patches of the multiverse. These would be profoundly different. Different laws of physics, different constants, different structure. We should not be able to see them. Our light cones do not overlap. Yet if there are subtle connections, if the boundaries are not perfect, if quantum tunneling occurs between universes, we might detect signals, faint, strange, unexplainable by physics in our universe. JWST was not designed to see beyond the horizon, but it might be doing exactly that, detecting signals that should not exist, from places that should not be observable, from times before time, from outside space. The data is preliminary, the interpretations are uncertain, but the signals are real, and they demand explanation. Explanations that might require rethinking everything we know about cosmology, about the universe, about the limits of what can be observed. JWST opened a window, but what lies beyond the window is not what we expected, not galaxies, not stars, but something stranger, something that should not be there, something that might not be part of our universe at all. JWST, it was looking for galaxies, stars, black holes, objects we understand. What it found includes objects we do not understand, structures that do not fit any category, not galaxies, not quasars, not supernovae, just unidentified. They appear in multiple fields, multiple observations, consistent features, real detections, not artifacts, not noise. Something is there, but we do not know what. These structures are large, spanning thousands of light years, sometimes more. They emit light across multiple wavelengths. Infrared, visible, sometimes ultraviolet. The spectra are unusual, emission lines that do not match known elements, or ratios of lines that make no sense, forbidden transitions, combinations that should not occur. One structure, designated JWST, anomaly 001, appears as a ring, perfectly circular, 50,000 light-years in diameter, no visible center, just a ring of emission, glowing uniformly. No stars, no gas clouds, no apparent source. The ring sits at redshift 8, distance of about 12 billion light-years. It existed when the universe was less than 1 billion years old. Nothing we know creates rings like this. Supernova remnants form rings, but they are small, a few light-years across. They fade. This ring is enormous, Persistent across multiple observations, gravitational lensing creates rings, Einstein rings. When a massive object bends light from a background source, the alignment has to be perfect. The geometry has to be exact. Lensing could explain some rings, but not this one. There is no lensing mass, no foreground galaxy or cluster, no gravitational distortion, just the ring. Alone. Impossible. Another structure appears as a line, straight, thousands of light years long, thin, glowing, crossing the field of view. No curve, no bend, perfectly straight. This defies astrophysics. Natural objects are not straight. Gravity creates curves. Orbits, spirals, filaments, but not straight lines. Magnetic fields can align structures, create filaments, but even those curve, follow the field lines. This line is rigid, perfectly straight, as if drawn with a ruler. The spectra are wrong too. The light from these structures shows emission lines at wavelengths that do not correspond to known elements. Some researchers think these are redshifted lines from known elements, but the redshifts do not match. Lines from oxygen should be at one redshift, lines from hydrogen at the same redshift, but they are not. Different lines show different shifts, as if the object is at multiple distances simultaneously. This is impossible, unless the structure has velocity gradients, different parts moving at different speeds. But the velocities required are enormous, thousands of kilometers per second. Across the structure, nothing holds together with that kind of internal motion. It would tear itself apart. Yet there it is, stable, persistent. Another anomaly shows variability, brightness changing over months, dimming, then brightening, then dimming again. The timescale is wrong for stars. Stars vary on days or years, not months with this regularity. Quasars vary, but irregularly, chaotically. This variation is periodic, regular, like a signal. Some astronomers joke it is a beacon, an intentional signal from an advanced civilization. This is not serious, but it illustrates the confusion. We have no natural explanation, no astrophysical process that produces this pattern. Then there are structures that appear three-dimensional, not projected on the sky, but extending in depth, creating shadows, occulting background objects, as if they are physical barriers, but transparent, letting some light through, blocking other wavelengths. This suggests complex structure, layers, composition varying with depth, but made of what? Gas would disperse, dust would clump. Solid matter at these scales is impossible, yet something is there, with depth, with structure. Some researchers propose these are dark matter structures, pure dark matter without any baryonic component. Dark matter halos that somehow emit light, or bend light in unusual ways. But dark matter does not emit, does not interact electromagnetically. That is its defining feature. Unless our understanding is wrong, unless dark matter has weak electromagnetic interactions we have not detected. This would revolutionize particle physics. But it is one possibility. Others suggest these are topological defects, cosmic strings, domain walls, exotic structures from the early universe, predicted by some theories, never observed. If they exist, they would be invisible normally, detectable only through gravitational effects. But maybe JWST is seeing them indirectly. Light interacting with the defects, scattering, creating patterns. This is speculative. No model predicts exactly what JWST sees, but it is an attempt to explain the unexplainable. There are also suggestions of extra-dimensional structures. If extra dimensions exist, if they are not compactified perfectly, they might have observable effects. Structures existing partially in our dimensions, partially in others, appearing strange, defying three-dimensional physics. String theory allows this. Brain world scenarios allow this. But we have no confirmed evidence for extra dimensions, just the math, and now possibly the observations. Some of the structures show what looks like organization, patterns, symmetries. This is deeply unsettling. Natural objects are rarely symmetrical, occasionally spherical due to gravity, sometimes spiral due to rotation. But these structures show artificial-looking patterns, hexagonal arrangements, grids, regular spacing. This could be coincidence, pareidolia. Humans see patterns everywhere, even where none exist, but multiple researchers independently note the same features, the same regularities. It is hard to dismiss entirely. The most disturbing possibility is that these are not objects at all, that they are something else. Glitches in space-time, regions where the laws of physics differ, where constants have different values. These would appear strange, emit light in unusual ways, have spectra that do not match our understanding, because our understanding applies to our space-time, not to these regions. If the universe contains pockets where physics is different, where symmetries are broken differently, where particle masses vary, those pockets would look like nothing we have seen before. JWST might be detecting exactly that. Windows into different physical regimes, islands where reality operates by different rules. This is not mainstream. Most astronomers think the structures are ordinary, just poorly understood. Exotic astrophysical phenomena we have not encountered before, new types of supernovae, unusual nebulae, rare configurations of matter and energy. As more data accumulates, as models improve, the anomalies will be explained. But for now, they remain unidentified. Structures in the cosmos that we can see, that we can measure, but that we cannot explain. Objects that should not exist, patterns that should not form, signals from something outside our understanding. JWST was supposed to answer questions. Instead, it raised new ones, deeper ones, more troubling ones, and the answers are not yet clear. General relativity predicts time dilation. Clocks run slower in strong gravitational fields. They run slower for objects moving at high velocities. This is not theory. It is observed. GPS satellites account for it. Particle accelerators measure it. Atomic clocks confirm it. Time is relative. It flows at different rates depending on conditions. In cosmology, time dilation affects how we see distant objects. A supernova in a distant galaxy appears to evolve slowly. Its light curve stretches. What takes days in the supernova's rest frame takes weeks or months in our frame. The farther away, the greater the dilation. This is understood, measured, predicted accurately by relativity. JWST observations show something different, time dilation that does not match predictions. Objects evolving at the wrong rates, too fast or too slow, inconsistent with their redshifts. One example is high redshift supernovae. JWST has observed several. Type 1, A supernovae are standard candles. They have known luminosities, known light curve shapes. We can predict how they should look at any distance. At redshift 8, a supernova should appear slowed by a factor of 9. What takes 20 days in the supernova's frame should take 180 days in ours. But JWST sees supernovae at redshift 8 evolving in 60 days, 1/3 the expected time. The time dilation is wrong, too small, as if the universe is not expanding as much as we think, or as if relativity is wrong at cosmological scales. Neither option is comfortable. The expansion is measured independently. The Hubble constant, the cosmic microwave background, baryon acoustic oscillations, all agree. The universe expands at a specific rate. Time dilation should follow from that rate. Yet JWST's supernovae do not match. Some researchers suggest dust. Dust dims light, makes distant objects appear fainter and thus farther than they are. If the supernovae are closer than we think, the time dilation would be less. But spectroscopic redshifts confirm the distances. The supernovae are genuinely at redshift 8, not closer. Another suggestion is that type 1a supernovae were different in the early universe, that their light curves had different shapes, that they evolved faster intrinsically. But type 1, supernovae are thermonuclear explosions, white dwarfs accreting matter until they reach a critical mass, then exploding. The physics is universal. The timescales are set by nuclear reactions. These should not change with cosmic epoch. There are also quasars showing anomalous time dilation. Quasars vary. Their brightness fluctuates. The variability timescale tells us about the size of the emitting region. Fast variations mean small regions. Slow variations mean large regions. At high redshifts, quasar variations should appear slowed, stretched by time dilation. JWST sees quasars at redshift 10, varying on timescales of weeks. This is days. Reasonable. But time dilation should stretch it to months. It does not. The variations are too fast, as if time dilation is not operating, or operating differently than predicted. Then there are gamma-ray bursts. GRBs are the brightest explosions in the universe. They flash, bright for seconds or minutes, then fade. JWST has followed up several high-redshift GRBs, observing the afterglows. The afterglow-like curves should be stretched, evolving slowly due to time dilation. But they evolve at normal rates, as if they are nearby. Yet redshift measurements confirm they are distant. The discrepancy is consistent across multiple GRBs. Not a fluke. Not one bad measurement. A pattern. Some cosmologists suggest this indicates a problem with the cosmological model, that lambda CDM is wrong, that the universe does not expand uniformly, that local inhomogeneities affect time dilation in ways we have not accounted for. This is radical. Lambda CDM is tested extensively. It fits observations of the CMB, large-scale structure, supernova distances, everything except these JWST anomalies. Others propose modified gravity. That general relativity breaks down at cosmological scales. That time dilation does not follow Einstein's equations exactly. Modifications would alter predictions, could explain the discrepancies, but we have no confirmed deviations from general relativity yet. Every test has confirmed Einstein's theory, from solar system scales to gravitational waves. Why would it fail only for cosmological time dilation? Then there are suggestions involving the cosmological constant, dark energy. If dark energy is not constant but evolves, it could affect time dilation, change how the universe expands, alter the relationship between redshift and cosmic time. This requires dark energy to have been different in the past. More precisely, to be evolving in a specific way that matches the anomalies. Models exist, but they are contrived, designed to fit JWST data, not predicted beforehand. Another possibility is that we are misidentifying the objects, that what we think are high redshift supernovae are something else, closer objects with unusual properties. But spectroscopy confirms the redshifts. The host galaxies are distant. The supernovae are within those galaxies. They are genuinely far away. Some researchers invoke quantum gravity. At cosmological scales, quantum effects might influence spacetime, alter how time flows, create variations in time dilation that classical general relativity does not predict. This is highly speculative. Quantum gravity does not have a complete formulation. We do not know what it predicts, but it is an avenue some theorists explore. There are also anomalies involving gravitational time dilation near black holes. JWST observes accretion disks around high redshift quasars, material spiraling into supermassive black holes. The inner regions orbit close to the event horizon. Relativistic speeds, extreme gravity, time dilation should be enormous. Light from the inner disk should be redshifted, stretched. The spectral features should broaden. This is observed in nearby quasars, but in high redshift quasars, the broadening is less than expected, as if time dilation near the black hole is weaker, as if gravity is not as strong as it should be. This makes no sense. Black holes are black holes. Their properties are determined by mass and spin, not by cosmic epoch. A billion solar mass black hole at redshift 10 should behave the same as a billion solar mass black hole nearby. Yet JWST suggests differences. The most exotic explanation is that time itself is different, that the flow of time in the early universe was not the same as now, that clocks literally ran at different rates, not due to dilation, but intrinsically. This would require new physics, a scalar field coupling to time, a modification to the metric tensor, something beyond standard general relativity. No such theory is widely accepted, but the observations might force us to consider it. JWST's time dilation anomalies are some of the most troubling findings. They question our understanding of relativity, of cosmology, of time itself. If confirmed, they require revisions to fundamental physics. If explained away, they demand understanding subtle systematic effects we have not identified. Either way, they represent a mystery, one that goes to the heart of how the universe works, how time flows, how reality evolves. JWST sees time behaving strangely, and we do not know why. Every telescope detects noise, cosmic rays hitting the detectors, thermal fluctuations, electronic glitches. Standard procedure is to filter this out. identify artifacts, remove them from the data, leave only real astronomical signals. JWST has sophisticated filtering algorithms, designed by experts, tested extensively. They work. Most noise is removed. Most artifacts are identified. But some signals pass through the filters. Consistently. These are not noise, not artifacts. They are real detections, but they do not correspond to any known astronomical object. The telescope sees something, but there is nothing there. These are the phantom signals. One type appears as faint point sources, stars or distant galaxies. But when you observe them again, they are gone. Not variable, not transient, just vanished, as if they never existed. Follow-up observations show empty fields, no object at those coordinates. Yet the original detection was clear. Multiple pixels, above noise threshold, real signal. Other telescopes cannot confirm them. Hubble looks at the same coordinates, sees nothing. Spitzer saw nothing years ago. Only JWST detects these phantoms, then loses them. This could be instrumental. Something about JWST's detectors creating false signals under specific conditions. But the signals appear across different detectors, different filters, different observation modes. If instrumental, the artifacts should be consistent, predictable. These are random, distributed across the sky. Another phantom type is extended emission. Diffuse glows spanning large areas. No apparent source. Not nebulae, not galaxy halos, not scattered light from foreground objects. Just uniform emission. Faint but measurable. These regions show up in infrared, JWST's primary wavelength range, but they are absent in visible light. Hubble observed the same fields, saw nothing. The emission is unique to JWST, as if something invisible to other telescopes becomes visible in specific infrared bands. The spectra are featureless, no lines, no features, just a continuum, a flat emission across wavelengths. This is unusual. Most astronomical sources have spectral features, emission lines from gas, absorption lines from stars, thermal emission with a blackbody curve. These phantom glows have none of that. Just flat, uncharacteristic. Some researchers think it is zodiacal light, sunlight scattered by dust in the solar system, close to Earth, bright in infrared. But zodiacal light has a known distribution, a predictable pattern. It varies with the telescope's position. These phantom glows do not match. They appear in random fields, unconnected to ecliptic latitude, unconnected to solar angle. Then there are the flickering pixels, individual detector pixels that flash, brighten briefly, return to normal, not cosmic rays. Those create different signatures, not hot pixels. Those are constant. These are intermittent, random, occurring across the detector array. Statistical analysis shows the flickers are not random noise. They cluster, appear in patches, as if something is activating multiple pixels simultaneously, not one at a time like noise would, but in groups, patterns. This suggests a real signal, something hitting the detector, something producing photons. But what? One hypothesis is dark matter. If dark matter particles interact with the detectors, they could produce faint signals. WIMPs scattering off silicon atoms, depositing tiny amounts of energy, creating electron-hole pairs, registering as photons. This is the principle behind dark matter direct detection experiments. JWST is not designed for this, but it is sensitive enough. If dark matter interactions are slightly stronger than predicted, JWST might detect them. Accidentally, the flickering pixels could be dark matter events, random, distributed across the detector, creating the patterns we see. This is speculative. No dark matter detection experiment has confirmed WIMPs yet. JWST seeing them would be groundbreaking, but also questioned. Extraordinary claims require extraordinary evidence. Another possibility is neutrinos. Neutrinos interact weakly, mostly pass through matter without effect. But occasionally they scatter, deposit energy. JWST's detectors are large, exposed to the neutrino flux from the sun, from cosmic rays, from supernovae. Most neutrinos pass through, but a few might interact, create signals. Neutrino interactions are well understood. The predicted rate is low, too low to explain the number of flickers JWST sees. But if neutrinos have interactions we have not discovered, if there are sterile neutrinos or right-handed neutrinos coupling differently, the rate could be higher. Then there are suggestions of quantum phenomena. Virtual particles, vacuum fluctuations. In quantum field theory, the vacuum is not empty. Particle-antiparticle pairs constantly appear, annihilate. Normally this is unobservable. The pairs exist too briefly. But in strong electromagnetic fields, the pairs can be pulled apart, become real. Could JWST detectors create fields strong enough? Could the electronic readout process generate virtual particles that occasionally become real? This seems far-fetched, but quantum mechanics allows strange things. Some physicists joke that JWST is detecting ghosts, not literal ghosts, but quantum ghosts, virtual particles flickering in and out of existence, captured occasionally by the detectors. This is not serious, but it illustrates the confusion. We have no good explanation. The most disturbing signals are the ones that repeat, not randomly, but at specific intervals, every 27 days, or every 13 hours, or other periods, as if something is on a schedule, transiting, orbiting, pulsing. But there is no source, no object at those coordinates, just empty space. Yet the signal returns, precisely, regularly, like a clock. Some astronomers have checked whether these periods match known phenomena. Earth's orbit, the Moon's orbit, Jupiter's moons, pulsar periods. Nothing matches. The periods are unique, not corresponding to any solar system object, not corresponding to any known astrophysical cycle. One signal repeats every 13.2 hours, precisely, for months. Every observation catches it. Same brightness, same wavelength, same location in the field. But there is nothing there. No star, no galaxy, no asteroid. Just the signal. Appearing, disappearing, returning. This could be a calibration artifact, something about how JWST operates. But the period does not match any operational cycle. The telescope does not repeat observations on 13.2-hour periods. The data processing does not introduce 13.2-hour rhythms. It is a mystery. The phantom signals are not publicized widely. They are discussed in technical papers. Among specialists, most assume they will be explained eventually. Instrumental effects, subtle systematic errors, unusual but mundane causes. But as time passes, as more data accumulates, the phantoms persist. They do not go away. They do not resolve into known objects. They remain phantoms, detections of something, but something we cannot identify, cannot explain, cannot confirm. JWST sees signals from nowhere, hears whispers from the void, and we do not know what is speaking. Voids are empty regions of space, low density, few galaxies, little matter. They form naturally in cosmic structure. Matter clumps into filaments and clusters, leaves behind voids. The cosmic web. This is understood, simulated, observed. Voids are normal, expected. But JWST sees voids that are not normal, not expected. Voids with structure, organization, patterns that should not exist. One void spans 200 million light-years, containing almost no galaxies, almost no visible matter. But JWST detects faint emission throughout the void, not point sources, not galaxies, diffuse light, spread across the entire volume, as if the void is not empty, as if something fills it, something that glows. Spectroscopy shows the emission is redshifted consistently. The entire void sits at the same cosmological distance. The light is not from foreground contamination. It is genuinely from within the void. But what produces it? Gas in voids should be cold, dark, undetectable. Stars form in dense regions, not in voids. There should be nothing there to emit light. Yet JWST sees emission, faint, but measurable, across a volume larger than the largest superclusters. Some researchers suggest it is intracluster light, light from stars stripped from galaxies, wandering through space, filling the void. But intracluster light is faint. You need dense environments, galaxy clusters, lots of interactions. Voids do not have this, they are defined by their emptiness. Another suggestion is dark matter annihilation. If dark matter particles annihilate when they collide, they produce photons. Standard WIMPs annihilate too rarely to produce detectable light, but some dark matter models predict higher annihilation rates. If those models are correct, voids could glow, faintly, from dark matter decaying or annihilating. JWST might be seeing this. Direct evidence of dark matter interactions. This would be monumental. But it requires dark matter to behave differently than most models predict. Then there are the void filaments, structures within voids, thin threads connecting across the empty space. Not matter filaments. Those exist between voids. These are inside voids, crossing through the emptiness. They show up as linear features, long, thin, glowing faintly, made of something. But what? Simulations do not predict structures inside voids. Voids form because matter evacuates those regions, falls into denser areas, leaves the void empty. There should be no filaments inside. Yet JWST sees them. Multiple voids, multiple filaments. Always the same pattern. Long threads, crossing the void, connecting nothing to nothing. One hypothesis is that these are cosmic strings, topological defects from the early universe. If cosmic strings exist, they could stretch across voids, invisible in most wavelengths. But perhaps JWST's sensitivity reveals them, through some mechanism we do not understand. But cosmic strings should be gravitationally detectable. They warp spacetime, create lensing. The void filaments show no lensing signature. If they are cosmic strings, they are extraordinarily light, far lighter than predicted. Another hypothesis is magnetic fields. Voids are not completely empty. They contain trace gas, ionized plasma. This plasma can carry magnetic fields. If the fields are strong enough, they could confine charged particles, create synchrotron emission, glow in infrared. But the fields would need to be very strong, stronger than any observed in voids before, and somehow organized into filaments. This seems unlikely but not impossible. Then there are the void galaxies. Galaxies deep inside voids, far from any other galaxy. Isolated. These are rare but known. A few have been found. JWST finds more. But these void galaxies are strange. They are too luminous, too massive. Galaxies in voids should be starved. No gas infall. No nearby companions to merge with. No fuel for star formation. They should be small, dim, dying. But JWST's void galaxies are bright, active, forming stars, as if they have abundant gas, as if they are thriving in the emptiness. Where does the gas come from? Galaxies are not isolated systems. They accrete gas from the intergalactic medium. But voids have little intergalactic gas. It was evacuated, fell into denser regions. Void galaxies should have exhausted their internal gas long ago. Yet they shine, form stars, produce light, as if supplied by an invisible reservoir. Some researchers propose that dark matter halos in voids are different, that they are denser than expected, that they funnel gas efficiently, that void galaxies receive cold flows of gas from unexpected directions. This is possible, but unconfirmed. Simulations do not show this clearly. Then there are the void walls, boundaries of voids, where the empty region meets the filaments. These walls should be thin, just the edge of the density gradient. But JWST sees thick walls, structures spanning millions of light years, surrounding voids like shells. These walls glow, emit infrared, contain galaxies, but also something else. Diffuse emission, not associated with galaxies, spread throughout the wall, creating a bubble around the void. This is unexpected. Walls should be where matter accumulates, galaxies, gas, dense regions. But this additional emission suggests something else, something filling the wall, something we do not recognize. One exotic proposal is that voids are not empty because dark energy is not uniform. That dark energy concentrates in voids, that it has structure. In standard cosmology, dark energy is a cosmological constant, uniform everywhere, same density in voids as in clusters. But some modified theories suggest dark energy can clump, can vary in density. If it does, it might concentrate in voids, fill them with invisible energy. This energy could affect how light propagates, could produce secondary emission, could explain the glow JWST sees. This is highly speculative. No confirmed evidence for varying dark energy, but the observations might provide that evidence. Another possibility is that voids contain primordial magnetic fields, fields from the early universe, stretched by cosmic expansion, filling voids uniformly. These fields would be weak, but vast, spanning the entire void. Charged particles moving through the fields would radiate, produce faint synchrotron emission. JWST might be detecting this, the first direct observation of primordial magnetic fields. The void structures challenge our understanding of cosmic voids. We thought they were simple, empty, boring. Just the spaces between interesting structures. JWST shows they are not empty, not simple. They contain structures, emission, organization, things we did not predict, things we cannot fully explain. The voids might be more important than we thought. Not just empty space, but active participants in cosmic structure, regions with their own physics, their own dynamics, their own mysteries, and JWST is revealing them, one strange glow at a time. JWST has been operational for less than 3 years. Already it has found more anomalies than any telescope in history: impossible galaxies, strange light, time dilation errors, phantom signals, void structures. Each observation raises questions. Each discovery challenges models. Some will be explained. Instrumental effects, calibration errors, misinterpretations of data. This always happens with new instruments. Initial results are uncertain, refined over time, corrected, understood. But some might be real. Some might represent genuine cracks in our understanding. New physics, new phenomena, new aspects of reality we have not encountered before. The impossible galaxies are being taken seriously. Hundreds of papers have been written. Theorists propose modifications to galaxy formation models, alternative dark matter scenarios, changes to the initial conditions of the universe. Some models work, they fit the JWST data, but they require adjusting parameters, fine-tuning, inventing new mechanisms. This is how science progresses. But it also raises concerns. Are we patching broken models, or genuinely learning? The time dilation anomalies are harder to dismiss. Time dilation is fundamental, predicted by relativity, tested extensively. If JWST observations are correct, if time dilation at high redshifts does not match predictions, something is deeply wrong, either with general relativity, or with cosmology, or with how we measure distances and redshifts. All options are uncomfortable. All require revisions to well-tested theories. More data is needed, more observations, more supernovae, more quasars, more checks. If the pattern persists, if the anomalies remain, we will face a crisis, not a small problem. A fundamental breakdown of our framework. The phantom signals are intriguing, possibly instrumental, possibly real. If real, they could be dark matter. Neutrinos, quantum effects, or something entirely new. Particles we have not discovered. Interactions we have not predicted. JWST was not designed to detect dark matter, but it might be doing so accidentally. If confirmed, this would transform particle physics, provide the first direct detection of dark matter particles, reveal their properties, open new research directions. The void structures are the most mysterious. We have no good explanation. No model predicts glowing voids. No theory explains the filaments. The observations might be errors, systematic biases, foreground contamination. But they persist. Different fields, different observations, different analysis methods. If they are real, they tell us voids are not simple, not empty. They contain something. Dark matter behaving unusually, dark energy with structure, magnetic fields from the early universe, or something we have not imagined. Each possibility requires new physics. Each demands rethinking what we know. What does it all mean? It means JWST is doing what it was supposed to do, pushing boundaries, finding unexpected things, challenging assumptions. Great telescopes always do this. Galileo's telescope revealed moons around Jupiter, contradicted Aristotle, required new models. Hubble found galaxies beyond the Milky Way, showed the universe is expanding, changed cosmology. Hubble Space Telescope found dark energy, revealed accelerating expansion, shocked physicists. JWST is following that tradition, showing us things we did not expect, things that do not fit, things that demand explanation. Some of what JWST sees will be explained within current physics. Exotic, but understandable. Rare phenomena we have not encountered before, but operating by known rules, fitting within the standard model, within general relativity, within lambda CDM cosmology. Other findings might require new physics, extensions to the standard model, modified gravity, new fields, new particles, new forces. This is exciting. This is how revolutions happen. Not by confirming what we know, but by finding what we do not. There is also the possibility that some observations are wrong, that JWST has systematic errors we have not identified, that the data is contaminated, that the calibrations are off. This must be considered. New instruments are complex. They behave in unexpected ways. Early results are uncertain. It takes years to fully understand a telescope, to trust its data completely. JWST is young, still being understood, still being calibrated. We should be cautious, but we should also be open to the possibility that the universe is stranger than we thought, that our models are incomplete, that reality at its extremes does not follow the rules we derived from nearby observations. The next few years will be critical. More data will accumulate. More observations will confirm or refute the anomalies. More analysis will identify systematic errors or validate strange findings. By 2030, we will know more. We will understand whether JWST has discovered new physics, or whether it has simply revealed how subtle instrumental effects can mimic revolutionary findings. Either way, we will learn, knowledge will increase, understanding will deepen. For now, JWST has shown us something outside our expectations, galaxies that should not exist, light from impossible times, signals from nowhere, structures in emptiness. It has captured images of the universe as it was, and as it should not have been. The telescope looks backward in time, to the early universe, to the first galaxies, to the era when stars began. But what it sees does not match what should be there. The past is not what we predicted. The early universe is not what we modelled. Something is different, something is strange, something is outside our current understanding. Whether it is outside space and time is unclear, but it is outside our physics, beyond our theories. In a realm we have not yet mapped, JWST opened a window. Through it, we see mysteries, anomalies, questions. The answers will come, with time, with effort, with careful science. But the journey has just begun. The telescope is young, the observations are preliminary, the strangeness is real, and we are only starting to understand what it means, what it reveals about reality, about the universe, about the limits of human knowledge. JWST has captured something we cannot yet explain, something that might change everything, or might be nothing. A glitch, an error, a misunderstanding, we do not know yet, but we are looking, and what we see is extraordinary.